interested only in a place where we to simplify a certain construction, and so the more exciting construction, at least from my point of view and for the problem I'm going to state, I can now spend more time explaining on. And so we'll start with, well, I can actually just skip this. So just for the people that weren't here, it's just the realization space, and somehow we had this in many different guises, but it's just I write down the vertices, the vertex coordinates of the polytopes that are combinatorially equivalent to my given polytope. Okay, and we already had this. What are the polytopes with the smallest realization space? Well, these are the projectively unique polytopes, right? For any admissible projective transformation applied to my polytope, the new polytope is again combinatorially equivalent, so it cannot get smaller. So these are the projectively unique polytopes, right? And we already saw some examples, right? So for example, a polytope with at most d plus 2 vertices, a deep polytope with at most d plus 2 vertices is projectively unique, right? And we also saw that some of this is tight, for example, in dimension 2. And then we have, for example, again, the dual of any projectively unique polytope is projectively unique. It's also easy. A simplicial polytope with more than d plus 2 vertices is not projectively unique. We will see later why. It's just a simple dimension argument. Then there is something more surprising. So while d plus 2 vertices are not projectively unique, well, if you are simplicial, then you can still have projectively unique polytopes with exponentially many vertices in D. So I think the number is roughly something like 3 to the D divided by 3 rounded down, but that's not really important. Then there is something that I liked a lot when I first read into the subject. And so there are projectively unique polytopes that, while realizable in Euclidean 8-bits, are not realizable with rational coordinates. And in the talk before, what follows from the talk before is that somehow for every finite field extension over Q, there is a polytope that you will not be able to, a projectively unique polytope that you will not be able to realize over this, in the vector space over this field. Okay. But this is somehow all high dimensional, right? So the polytopes that we saw in the last talk, they were of a huge dimension. So what we did, we started with some algebraic polytope, we added some points, and then we lifted them basically using the subdirect cone lift and the Lorentz extension, which gives you a huge dimension in the end. Okay? And we also saw this Anna mentioned this theorem of Below and Dobbins. But what they achieved was only that they fixed basically the face in a projectively unique way. The polytope that sits above this face is not projectively unique. It also has a big realization space. So there is a natural question, how many projectively unique polytopes in dimension D are there? And here's a conjecture that was first stated by Perles and Shefford in '74, and then again by Kalai in some conference band, and then he also posed this conjecture to me at some point, which is how I got into the project. So for each fixed D larger to equal to 2, the number of distinct combinatorial types of projectively unique D polytopes is finite. And the motivation was basically a strong universality theorem. This is a conjecture that I will get to in the end. Okay, but let's just first try to get this in. So I want to know whether for a fixed D, like 4 or 5 or 10,000, the number of projectively unique polytopes is finite. Can I maybe even enumerate them? Can I classify them in a nice way? And what I will argue now is that this is wrong. But let's say first why it is actually true in low dimensions, right? So the dimension space of the realization space of a polygon is just 2 times the number of vertices, right? Every vertex can move in 2 directions. It's also, again, easy. The dimension of every simplicial polytope, D polytope, sorry, is just by the same reasoning as D times F0 of P. And this is also an upper bound for all polytopes. Okay. If you want to be more precise, well, dimension 3, you can still compute the dimension of the realization space, really. And this is a really nice theorem. It comes up again in Koeber and Reeves-Thurston and so on, but it's basically just, if you want the dimension of the realization space, then you just have to count the number of edges and add 6. That's it. Okay, why is this relevant? Well, if I have a projectively unique polytope, then its dimension can be at most the dimension of the projective linear group. Okay? In particular, I can try just for the low-dimensional cases. So for 2 polytope can be projectively unique, only if 2 times f0 is 8. So I can have only triangles and quadrangles. And a 3 polytope can be projectively unique only if number of edges plus 6 is equal to 15, which also gives me, I can write down the list, it's just 4 of them. Okay? This also holds for simplicial polytopes, right? So we already saw that more than d plus 2 vertices for projectively unique polytopes are not, for simplicial polytopes are not projectively unique. And we have the converse as well, and you might conjecture that somehow this, or you might think at first that somehow this, that you can have the converse as well, but this is very wrong. But somehow, let me not get into this. So it's not true that if the dimension of the realization space is small, then it's projectively unique, but I will basically argue along these lines, so let's not go into this too deeply. Okay. What we have as a corollary now is that the number of projectively unique polytopes in dimension 2 and 3 is finite. Okay? But here's the results. If you go high enough, for each d larger or equal to 69, and it's actually like, so we can improve this to like 36, but it's not 4. It's the only thing that's relevant here. There exists an infinite family of combinatorially distinct d-dimensional polytopes with, well, linear number of vertices, and, well, they're all projectively unique. So surprisingly, this conjecture is, so this theorem is very hard to prove. When I was working with Arnaud, I was very happy because this conjecture of Shepard was very easy to falsify, but this was very hard.
And the number of vertices increase when the
Yes, of course, because every d polytope has at least d plus 1 vertices. Right? So I mean, you want to at least have an affine basis. This is why you have to increase the number of vertices here. Okay, so one idea. So a transmitter polytope is one of the central tools in the proof of Richter-Gibbert's universality theorem. So it works like this. It is a polytope, actually a 4 polytope with 2 sides, a special phase, and an input and an output. Once the input is determined, the output is determined up to projective transformation. Okay? So here's the thing. So the input phase is the lower phase, and the output phase is the upper phase. Okay? So one idea is, to prove this conjecture is, well, if I determine the input phase, then the output phase is determined. Then but then I can do connected sum with this output phase and make it a new input phase, right? And stack them onto each other. This is a very naive idea, but of course it's wrong. Why? Because I can still move the whole thing like an accordion, right? So this is not projectively unique. But it's a good idea. And we just have to refine it. So let me consider C just as the unit cube tiling. So just the infinite polytopic complex that covers R3 with vertex at the integers. And let me define some subcomplexes. So CK is just, I look into the all ones direction, and I restrict just to vertices which have the interior product with the all ones vector between 0 and k. Okay? This is an infinite complex, but nevertheless, I have that it's not only that the later complexes, so CK with k higher than 2, are not only determined up to projective transformation, they are determined really in the realization once I fix the realization of CK minus 1. Okay? What's the reason? Well, if I pass from CK minus 1 to CK, I just fill in the last vertex of a cube, right? And the last vertex of a cube is easily seen to be just determined by the preceding vertices, right? So to reconstruct this vertex, I just have to intersect this plane with this plane with this plane. Okay? Okay. So of course, this complex is now infinite, right? But it's also periodic, so I can just factor out some symmetry. And it turns out that if you want to work with this lattice is nice and nice to work with. So we factor this out, and we have a finite polytopic complex. Okay? So now it's still true that that k is, if k is at least 2, is determined from tk minus 1 with the same argument. But we don't know that it's actually realized at all. So this is only conditioned on that we know that tk is in some way realized. But this is a hard part. So we have to realize T1 in R4 in such a way that tk exists, so tk building iteratively on T1. Oh, and it is also in convex position. So this is only, so this tk is just sorry? No, so this tk is just a homotopy equivalent to a 2 torus, but it's not a polytope, right? So what we want in the end is that if we take the convex hull, all the information in the boundary should survive somehow taking the convex hull, which means that tk should lie in the boundary of its own convex hull, right? So we will spend a lot of time just arguing that, so we can construct this complex tk, but if somehow the complex looks like this and we take the convex hull, then we lose all the parts that are in the interior, which is not good. Okay, so we want convex hull. Okay, so how do we build this? This is a rather hard part. So we see this as a kind of discrete differential equation. And somehow it's a discrete differential equation that has been studied a lot by people in discrete differential geometry who are interested in this for, well, a variety of purposes, visualization and so on. So the initial value for my PDE is just T1. So this is my starting complex. And the discrete PDE I want to solve is a discrete conjugate net. This is what basically the discrete conjugate net is just solving just adding the last vertex of the cube iteratively. So we want to, from T1, construct tk. This is basically it. So to show that this exists, that we can use several facts. So first of all, if we have a two-dimensional torus or something homotopy equivalent to a two-dimensional torus in R4, then we should realize it in a symmetric way, and there's a canonical way to do it. We just place the vertices on the Clifford torus. Or actually, we place it on several weighted Clifford tori and work then along the fibration given by Clifford tori. So this is just to make this setup nicely symmetric. So
I'm sorry, maybe you can explain how PDE come to this game.
Well, how can I wipe? So a conjugate net is somehow, it seems to be a very, very classical PDE that somehow that is not just studied that much anymore, right? It's just a map F from Rm to Rn, such that if I take for all I not equal to j, I have that delta I, delta j of f at any given point x lies in the span of delta I, f, and delta j, f at x. So if you think about this, you want that the second derivative, so you have like delta I f here, delta j, f, and then you want that the second derivative lies somewhere in the span. And at some point, this discrete differential geometry, people became interested into this kind of discrete problem because became interested in conjugate nets because they have a natural generalization or to the discrete, or they have a natural discrete analog, which is just saying that if I have an edge here and an edge here, then the remaining vertex of this quadrangle should lie in this span, which just means that it should be just planar. And they studied it, and it has several nice properties. It has, in dimension 2, it can be given a nice conformal structure, and then somehow in higher dimensions, this structure is automatically conformal, it's like discretely conformal, and then there is a nice property that we will actually use, so that these discrete conjugate nets are basically quartics. All right, so you can formulate it in this way: if in the notation I have there, if T2, all the vertices of T2 lie on some quartic, then all the vertices of TK lie in some quartic, in the same quartic. And some of this tells you where the vertices will lie. So we just use a lot of their information to know to pin down the vertices, to pin on our construction. Okay. So this is one of the third tool that we use, and then there are some smaller things. And then a second tool was that so you can generalize the Maxwell-Cremona conditions to manifolds with non-trivial first homology, or the Alexander von Eynort theorem to manifolds with boundary, to show that locally convex actually for our situation implies globally convex.
But there's no connection with projectively unique polytopes.
Well, there is, because so if T1 was projectively unique as a polytope complex, then TK would also be projectively unique, right? That's a connection. Okay. So, but if I have this also, if I have this setup that they are in convex position, then the convex hull of T1. If the convex hull of T1 is projectively unique polytope, then the convex hull of TK will be projectively unique polytope. Okay? So this is why. So the original idea, you remember, this was this. We want to say we start with a projectively unique phase, and then we add these transmitters onto it. And the idea would be that this is the result of this this large sum of transmitters is just projectively unique. Because the initial input is projectively unique. But this is just false. So this is just a refined idea. We start with something projectively unique, and then iteratively build on it. And this is basically, I mean, you can think of it this way. It's just, we are solving just the Cauchy problem. And the Cauchy problem for the conjugate net is just, it's just unique, the solution. Okay. Yes. Basically, we use a lot of their. Yeah. Okay. So now we build our complex. So I drew the two-dimensional example, which is a bad analog, because of course the new vertices that I will add here in every step are not determined, which is why these people like Alexander Bobenko, Ulrich Pinkhal, they studied these two-dimensional surfaces, but they have an additional condition on the ratio between this diagonal and this diagonal. And then they are unique, so they have an additional conformal structure. But in our higher dimensional case, it's just unique. And in this way, you build your surface, and you prove that there is such a structure, that building on T1, you can extend to TK as a polytope complex and in convex position. Okay, so if we can construct this in dimension 4, why can't we just solve the conjecture in dimension 4? Well, the point is that T1 itself is not projectively unique. It has too many vertices, for example. But it's also, I mean, so vertices is not, number of vertices is not like the only parameter, but it's not projectively unique. But we can use this we can use Lorentz extensions to kill the additional degrees of freedom we have in T1, right? And in the end, it turns out that it's not good to use just Lorentz extensions. You get a better result if you just use the subdirect cones. But then you're done. That's it. Okay? So let me close with just one problem. How many projectively unique 4 polytopes are there? Okay? But then the problem I was starting to look at and somehow I find more interesting is, well, do we have a strong universality theorem? So for those of you who don't know the universality theorem for polytopes, it says that for every semi-algebraic set, there is a polytope, or 4 polytope even, whose realization space is stably equivalent to it. Stably equivalent means in particular a multiple equivalent, but does not mean that the dimension, for example, is the same. So it could be a huge dimensional space. The realizations of a polytope, it's just homotopy equivalent. This is what we still know. It's somewhat stronger than homotopy equivalent, but it's somehow in the details. So what I don't know is if I fix the dimension larger equal to 4, of course, and I have any real, and so I can restrict to real algebraic sets, or I can go to primary semi-algebraic sets. I can ask whether there is actually a deep polytope such that, well, it's not always the whole realization space, but sometimes a nice subset like Zariski open and closed, Zariski open and dense, or something like that, is homomorphic, or, I mean, we could really ask for a birational equivalent to this S. Okay? And so this was also actually one of the purposes of constructing this polytope, because, of constructing these surfaces, because these are rigid transmitters. They don't add anything to the realization space. But I don't know how to fill in the rest, so maybe it's hard, maybe it's impossible, I don't know.
Nevertheless, is it possible to say what is topological property, because for y, for 5-dimensional, dimension 5 is good and 4-dimensional is bad. What kind of, well, you know, many examples in topology when you can distinguish dimensions.
Okay.
There is a concrete reason why, for example, Smale proof for Poincaré conjecture was more or less simple with comparison with Perelman. And
you mean this theorem of?
In your case, why 5 is better than 4?
So in my case, 5 is not better than 4. So here it doesn't. So it's just 69 is better than 4 because it's.
69 is better.
Yes.
This I can understand, but about 5 I don't.
This is you're referencing the theorem that Arnaud mentioned, that somehow if you have if you have any 3 polytope, then there is a 5 polytope that contains this as a projectively unique phase, right? Yeah. Well, this is somehow that's not so much about 4 or 5. It's just that you need 2 dimensions to rigidify this, or to do this, or to this rigidifying construction. So basically, so if you have a polygon, then if you have a polygon P, then there is a 4 polytope that contains this polygon as a projectively unique phase. Okay, so it turns out that going up 1 dimension is just not enough. Okay, you cannot fix it in 1 additional dimension. You need 2 additional dimensions to fix this structure.
So no any possible reduced dimension from?
No, it's not possible actually to do it in dimension d+1. No, no, they don't have, but somehow the polytopes we constructed that.
When you solve this differential equation, it preserves the field.
Yes, precisely. It's yeah.
But at the beginning, you don't have rational.
Well, somehow we can do rational, but then the dimension is like 200. So it's just bigger then. You can find such polytopes over any field you like. That's but that's easy.
Then maybe I ask one more. I'm a little bit confused about this the field. So suppose you have a projectively unique polytope over some algebraic extension.
Hmm?
And now you replace the algebraic member by a conjugate. So what happens? It could happen that that changes the combinatorial type.
What do you mean by?
So suppose you have a you have some algebraic number in the coordinates.
Hmm?
And you're saying so now what happens if you replace that algebraic number by conjugate number?
Hmm?
Another real root of that same irreducible polynomial.
Uh-huh.
Now, it could happen that this polytope is the same combinatorially, or it could be different.
Well, how do you make the polytope?
Maybe I'm confused about the notion of projectively unique.
Uh-huh.
So in particular, projectively unique means that whenever I
Ah.
substitute a conjugate, it actually has to change the combinatorial type.
That was I didn't understand.
Yeah, can you clarify this point? So there are two possibilities. If I build a polytope,
Hmm?
some field extension. Now there are only finitely many types for all real roots of that irreducible polynomial. But there are two possibilities, right? You could either be sort of projectively unique on the nose, or you could have a conjugate that happens to be combinatorially isomorphic.
Ah, I see.
As far as I have understood this, the idea to just isolate by the condition of convexity the one root.
That's what happened.
You-
Convexity nails
Exactly.
one of the roots.
Yeah.
And yes, actually, at least the same interesting question about the relation between the combinatorial, between the polytopal combinatorics and the algebraic properties of this.
But it's conceivable to have a polytope at the other end of the spectrum. So that maybe we have a field extension of degree, fully real field extension of degree 25,
Hmm?
such that all 25 roots give different polytopes. Right? That's also conceivable.
Yeah.
It could be interesting.
Hmm?
to build such
They should give somehow the same arrangement, but the complexity plays some interesting role.
I mean, I think you suggested once that you can also maybe use the Lafour construction to construct them, but then you only.
Construction is about this actually.
Yeah.
Because when you can see in the boundary complex, if you can recover from the boundary complex arrangement, and for projectively unique polytope you should be able something like this, then it is interesting to study this degeneration stuff,
Hmm.
and so it's by the work it should be responsible for the projective unique.
But I don't know. So the Lafour construction only gives you like that it's zero dimensional. It's finite, right? It's
Yes. So in the simplest case, it guarantees that it is just fine.
yeah.
Nothing more. So it doesn't tell you anything about algebraic properties, but
Yeah.
about the degrees of
Yeah.
And what about estimations? Are there some estimations of a number of projective when it's finite?
What? Ah, okay. I conjecture it to be like just infinite from dimension 4 on. It's just the construction does not work.
What's the largest number you know in dimension?
No. I mean,
Hmm?
for that case, you have dimension on which this is finite.
Yeah.
How many?
Well, it's just up to 3. It's finite. That's what I think. It's up between 4 and dimension 36. So here it's dimension 69, but really you can prove this is 36. It's not known. And
In dimension 4, what's the polytope with the largest number of vertices you know for this
it's, I think, the product of two triangles.
And is it now something simple about the problem of Christian Hansen? How much rational projectively unique polytope?
Well, this is also, it also gives you rational, but then you have to go up higher in dimension. It's like after dimension 200 or so, you can also get infinitely many rational projectively unique polytopes. So